Hello everyone, and welcome to this video where I'll be taking you through a sample question related to the objective, determine the derivative of a parametrically defined curve with polynomial and radical functions. So in this video, I'm going to be at Knewton.com in their Knewton Alta program. And I'm in this instructor mode, so it'll be a little different than what you're seeing as a student. I'm just going to go over one question from this particular objective, and hopefully watching me work on this will help you with all the very similar questions from that same objective when you're working on your own. All right, so here's the Knewton.com objective question. We'll see the answer in a minute. I'll work through it first. And if you're somewhat familiar with the topic at hand, I would highly suggest pausing the video first, working it out on your own, and then come back, watch me go through it, and compare your work to mine. See how you did, see how well you're grasping this material. All right. So this question, we're asked to determine the derivative of the parametrically defined curve represented by the equations. So we have x of t, so x depends on this the x coordinate of any position on the curve depends on this parameter called t, and it's calculated as 2t squared plus 5t plus 8, right, a polynomial in t. And the y coordinate of any position on the curve in terms of this t parameter is calculated -5 times t cubed minus 7 times t squared plus 6t plus 7, another polynomial. All right, so we're asked to, again, find the derivative. Remember this dy divided by dx, dy over dx. You could call it y prime of x. This was, the derivative of the curve, right? That's representing the slope of a tangent line, a line tangent to the curve that's represented by these equations, right? The curve traced out by these parametric equations here. Now, one way to do this, which would be quite difficult here, is you can try to eliminate the parameter. So that's where you rewrite the equation for the curve in rectangular form, right, with just x and y involved and not the parameter t. So you could try to solve one of these equations for t and substitute it into the other equation, get a rectangular equation, and then try finding y prime. And with this being a quadratic and a cubic polynomial of these forms, I would say that would be quite difficult. This is not impossible for over here. This is a quadratic. You could solve for t, get two different values for t in terms of x, but then it would make the y equals, once you substitute, really ugly, in my opinion. So there's a much, much faster way to do this, and what I'm going to do here with these polynomial equations, you would do in a very similar fashion with, radical functions involved as well. I'm assuming that you know how to find derivatives of polynomial and radical functions from any Calc 1 text course you've taken previously. All right. So here are the parametric equations, right? We had x of t is 2t squared plus 5t plus 8, and y of t was is negative 5t cubed minus 7t squared plus 6t plus 7. So again, as you change the values of t, these would trace out some curve on the xy plane, and we're asked to find, an expression that would help us determine the slope of any tangent line to that curve, right? dy over dx. All right. So I've shown this in other videos, so I'm not going to go through the whole development of this, but a very quick way to do this when we're in a single parameter here. Recall that, so again, hopefully from previous videos or whatever reading you're doing, if you want to find the derivative of the curve, the slope of the tangent line to the rectangular curve traced out by parametric equations, it's almost like we're dividing by dt. All right, you're not really doing that. There's this whole development for this, but dy over dx, this first derivative, slope of the tangent line, is equivalent to the following: dy dt, all right, so dy over dt in the numerator, divided by, and then dx over dt in the denominator, right? So again, it's like you're dividing by dt, even though technically that's not what you're doing. All right. We could call this, dy over dt, y prime of t, and this dx over dt, x prime of t. And those are very, very simple to find, being that these are polynomials especially. All right, so I'll go here. X prime of t, or dx over dt, is, applying the power rule here, would be 4t plus 5. And that's that. That'll be the denominator of this expression that's going to give us slopes of tangent lines on the rectangular curve. So 4t plus 5 in the denominator, and the numerator y prime dy over dt, and simple polynomial here, negative 15, t squared minus 14t plus 6. That'll go in the numerator of my derivative expression. So negative 15t squared minus 14t plus 6. And they may ask you to simplify things, but this is it. This expression right here will tell you the derivative, right, the slope of the tangent to the curve at any point, but you have to know the value of t that corresponds to that given point. That's the only thing. But you still get it, right? You still get the slope of the tangent line. You just need to know the value of t at that particular moment, at that particular point. And that's really it. So back to just to see the answer, verify negative 15t squared minus 14t plus 6, all divided by 4t plus 5. Exactly what I got earlier on paper. Wonderful. Yeah. And also, if you are, if you happen to be working in Knewton Alta's program on these homeworks, once you submit an answer, whether it's right or wrong, you'll be given some sort of answer explanation, right? General explanation as to why something was correct or why the answer was what it was. I would highly recommend reading through those explanations, whether you got it right or wrong, just to see how things are done, or maybe they do things in a different way than you did that you like better, or just just to verify that you understand the material, you understand why things are the way they are. Great. I hope this helps when you're working on similar problems like this on your own. And thank you very much for watching.